So again, now before actually seeing how to compute the solution, so how to we won't see specific algorithm for multi-agent reinforcement learning because this will require too much time and too much programming background and whatever. But before at least checking how to, let's say, design a solution, we must first check what are the kind of solutions we want to achieve. Okay. So we already said in single agent reinforcement learning that defining what kind of solution we want is trivial. In single agent reinforcement learning, you always have the same objective, regardless of the specific goal that your problem gives you. The goal of the agent is always to maximize the expected return. That's it. This may entail finding the shortest path toward the exit of a maze. This can entail be the first to cross the end line in a race car, whatever kind of specific task you may want to accomplish with your reinforcement learning agent. But from the point of view of the reinforcement learning algorithm, the objective, the goal is always to maximize the expected return. In multi-agent reinforcement learning, when we talked about the equilibrium selection issue, we said that basically this maximization of expected return may be no longer enough because we have multiple agents, and maximizes the global expected return tell us nothing about what are the individual expected return of all the agents. Okay, so simply this may not be the actual solution to aim for depending on our specific task. So to define the multi-agent reinforcement learning problem, usually you do need both a decision process model, okay, so the game or the environment, whatever you want to call it, but also a solution concept. So what kind of properties do I want for my solution? Okay, these usually are expressed in terms of properties of the joint policy. What is the joint policy? If you remember this slide that we've seen for the single agent world, in a multi-agent world, it is not that every single action of every individual agent has an observable effect on the environment. It can, but technically, more precisely, it is the joint action. So the collection, the summation of all the action of all the agents that have an effect on the environment. Let's simply imagine that I have a robotic warehouse, one of my robots drops an item in a shelf, and another robot picks up the item. The net effect on the environment is nothing, basically. The object was not on the shelf before and still is not on the shelf. But the two actions actually did something on the environment. Simply they combined to achieve a null net effect. So the fact that one agent drops the item and the other picks it up is a joint action. Okay? The combined effect of multiple actions. So a joint policy essentially is the policy of the collection, the union, the concatenation of all the policies of each individual agent. Okay? So usually in multi-agent reinforcement learning, if you want some specific properties about your solution, you express this property in terms of the joint policy. Okay? What properties? Well, we will focus on one, best response. We will mention Nash equilibrium and Pareto optimality. Welfare and fairness are just a reference if you want to know more. These are just examples of the additional properties we may want from our solution. Okay? And we are not forced to have some of these properties. We may have a problem to deal with in which we don't care about things like how is the reward distributed amongst our agent. We may deal with a problem in which as soon as one agent gets to the optimal policy among the many, we are fine. Okay, that's it. So we don't need any additional property. We want every agent to maximize the expected return, and we are fine. So let's try to see, I guess, one of these concepts. That is the most basic one, upon which, for instance, many other properties are usually built. So, best response, okay, in reference to a policy is defined as this. Given a set of multiple agents, okay, and we focus on the perspective of one of these agents, let's call it agent I, okay, and let's call all of the other agent policies pi minus I. Okay, so pi usually denotes a policy. Pi of I will be the policy of our agent that we are focusing on, agent I out of the many. Pi minus I are all of the other policies. This is just some notation, okay, to avoid too much text. Having a policy that is the best response means having a policy that maximizes the expected return while playing against a given set of policies. Okay, so we have, I don't know, 10 agents that are playing a game or whatever, focusing on one agent and defining its policy as the best response. So we want the agent to learn a policy that is the best response policy, will mean what? Assuming that the other agents have learned some policy, whatever policy, optimal, non-optimal, we don't care. Assuming that the other agents have learned or will converge to a given policy, any given policy, best response means we are playing to maximize the expected return against those policies. Okay? Our best response, depending on what other agents are doing, and this is something we cannot avoid in multi-agent reinforcement learning. So, depending on what other agents are doing, I'm maximizing my expected return. Okay? This will simply qualify a policy to be the best response. I cannot do better than this unless at least one of the other agents changes its policy. Okay? Assuming a fixed set of other policies, I cannot do any better. A best response policy may be not unique. Okay, so this is similar to the case to the example of the frozen lake scenario, in which the optimal policy was not a single unique optimal policy, but there were multiple paths that with the same length that brought to the goal. Okay, but best response is simply defined as this. We assume that we can fix the policies of other agents. What does it mean to fix the policy of other agents? Actually, we assume, for instance, that the other agents already finished learning. They have a fixed policy. They don't change the policy anymore. Okay? Then my policy is the best response if I cannot do any better against them. This is a general definition, okay, a general property that holds for any kind of games. Basically, you can define this best response for any kind of game. To understand better what does it mean to have a best response policy, okay? So just to clarify, we look at a specific example, the simplest that we can imagine. So a matrix game, zero sum. So tic-tac-toe, for instance, okay? We have two agents that are playing tic-tac-toe. What does it mean to play best response? In this specific case, two agents, zero sum, the best response can be called minimax policy. That is also the name of an algorithm to find this policy. Maybe in operation research or in optimization things you heard about minimax. Okay, so I had a funny video, but we will skip it. No, we will play it anyway. So This is just a reformulation of the general best response policy definition that we had in the previous slide in this specific case. The policy of agent I is optimized against the worst case, which means my opponent J is also playing best response. This is why we call it minimax. In a two-agent zero-sum game, if I playing best response for me means I am playing at the best as I can against an opponent that is also playing best as he can. This is minimax. Why? Simply because this is a zero-sum game. So my opponent has all the interest in defeating me, so in playing at best against me. I have the same interest, so we both play best response, aim to play best response. Some properties. Every two-agent zero-sum game has a minimax solution, so there is always this optimal policy. So for instance, do you need to deal with a specific problem in the real world that can be abstracted away as a two-agent zero-sum game? Okay, you know what you're aiming for. You're aiming for the minimax policy. You aim for your agent to learn the minimax because you know that that's the optimal policy. Okay, you don't have always this nice, clear objective, but this time you have this clear objective. Also, stochastic games, if they are zero-sum as a minimax solution. And a very good news is that you don't need to worry about issues similar to the equilibrium selection. If you find the minimax solution, that's fine. Even if there are multiple ones, they all yield the same return. So you're fine, basically. You don't need to take care about, I did find a minimax policy, but was it the best minimax policy? Yes. By definition, that's the best. So again, you already know minimax, but maybe not all of you. So this is a nice explanation that I found, so no reason to explain it in a worst way. This is an example, basically, about two agents playing tic-tac-toe, and the example gives you an impression of how first, what it means to play best response in this case. Second, this also gives you at the end basically the description of how the minimax algorithm works. Keep in mind that I anticipate one thing: the minimax algorithm works because you assume to have full knowledge over the game. Okay, so you know, for instance, the state transition function. I know that if I put a circle in the top left corner, then my opponent may put an X on the middle top corner, then I can put an X. I know what happens for any play. Okay? In that case, you don't need, strictly speaking, reinforcement learning. You can use dynamic programming, whatever algorithm you want. You know everything about the game. So this is not an example of how to solve the problem with reinforcement. So again, we have two agents. They are playing. The blue agent is the X. The yellow agent is the circle, and they are playing tic-tac-toe. So one example of two agents zero-sum game. How can they decide the optimal action at each decision step? So anytime it's their turn. Well, basically, what they can do is figure out, assuming that they know, but by saying this, now we don't listen to the audio. What are we doing by assuming that agents can distinguish if they won, if they lost, or if they drew? We are assuming that agents know the reward function. It is something that typically in reinforcement learning we don't have. Okay, so If the agents can do this, they know the reward function. A reinforcement learning agent would have no idea of this until when? Until it starts experiences terminal states. Look, I am the blue agent, I finished in this state and I lost. Okay, that's bad. I finished another time, another game, I finished in this state, I got a positive reward. That's good. That's when the reinforcement learning agent starts understanding what's going on. In a sense, starts understanding the reward function. It doesn't really model the reward function, but it starts understanding what are good policies, bad policies. Okay? Here instead we are assuming that the agent can do this from the very beginning. If the agent is able to do this, basically, okay, sorry, I was too quick. Besides doing that, the agent is also able to foresee what are the consequences of his actions. So, if I am in this state, agent blue, and I put a circle, or my opponent puts a circle in this corner, I end up in this state. Saying this means we are assuming that our agent knows the state transition function. Usually a reinforcement learning agent would have no idea about this. So it needs first to see the state. Okay? It cannot foresee the next state. So if an agent can do both, so distinguish when it is winning or losing, and distinguishing and foreseeing next states, this is the description of the min-max algorithm. Okay, so very easy algorithm. You can program this in Python easily, like I don't know, 20 lines of code probably. Well, in that case, if the agent knows both of these things, the agent can actually build what is called usually a decision tree, a game tree, a state tree, whatever. This is basically the state transition function. Okay. The blue symbol is an action, and in which state that action leads, with the expected reward I can get from the state. So let's try to analyze better this tree. Here, the agent blue is reasoning, right? He is trying to understand in which game states it will end up depending on both its moves, if I remember correctly, the blue agent has the cross, and the opponent moves, okay, that has the circle. So, the agent blue says, well, let's hypothesize that we put a cross here. That will be the new game state. From this game state, my opponent could do two admissible moves. Either put a circle here or put a circle here. In one case, I can put the cross and win. In the other case, I will be forced to put the cross here and withdraw. So, here I win. My payoff, my reward will be 1. Here I draw, my reward will be 0. This means that if the opposing agent puts a circle here, I am guaranteed to win, right? That's why, basically, how do I put numbers here? I take the numbers from the leaves, the terminal state, and I propagate them backwards. So, from here, I am guaranteed to win. So, the value, you remember the state value function? The value of this terminal state is 1. I won. The reward. You can put 5. Who cares? Okay? A positive reward. This means that the value of the previous state is also 1. Or positive. If we discount the values, like in reinforcement learning, this won't be 1. This will be like 0.9, whatever, depending on the discount factor. Now, why the value of this state is instead 0? Well, because in this state, I, the blue agent, I don't have the complete control of what happens next. If the yellow agent plays optimally, plays best response, he will not put the circle here, but he will put the circle there. And from here, the only possible outcome is a draw. Is it clear? So, the value of this terminal state is 0, a draw. The value of this state is 0. Why the value of this state is 0? Exactly because I, the blue agent, cannot assume what the other agent policy is, but I must assume that he is playing optimally. Okay, I'm a rational agent, I play against the worst case scenario. I must assume that the value for me of putting an X here is 0. At best, I can get a draw, assuming that the other agent is playing optimally. Right? Is this what a human agent does? Yes. You don't assume to play against a stupid opponent. You assume that you are playing against the best opponent there is in the world, so you must play the best as you can. In these states, the outcome is bad. In particular, if you look at the last, let's say, path, the last branch, here you can have both a very good outcome but also a very bad outcome. And again, your most rational strategy is to play against an enemy that plays off. So, for instance, this is not a very good game state. From here, unless my opponent makes mistakes, so unless the policy of my opponent is not the optimal policy, I can only draw at best. If you can do this, you know the reward function, you know the state transition function, you don't need reinforcement learning. You just, in a sense, plan ahead. Okay? You create this huge tree, and then you navigate the tree to find your exact optimal solution. The minimax algorithm guarantees you to find the optimal solution. Okay, so why we are talking about reinforcement learning if we can deal with this sort of stuff without reinforcement learning? Well, now imagine a real world problem in which this tree is huge. Huge means huge. Millions of possible states. Well, maybe it's true, minimax can give you the optimal solution, but maybe it can give you the optimal solution in 3 years of computation time. So, not very useful anymore. Just to draw some bridges again, maybe against other concepts that you already learned in other courses. Doing this sort of stuff, so creating this, expanding the states, this is the Markov decision process, okay? Do we agree that it is the depiction of the Markov decision process of this game? These are the states and the transitions between states. It's just a different graphical representation, but this is the Markov decision process. Actually doing this, navigating this graph, this tree, from the root to any leaf, is doing Monte Carlo tree search. Maybe you know, again, from optimization or optimization result, this is Monte Carlo tree search. Monte Carlo in reinforcement learning, what do you do? In optimization theory, you do this in a brute force way. You try to do this exhaustively. Let's navigate all of the branches. If you can do so, you usually need an heuristic, right? So a criteria to tell easily, okay, no, navigating these branches is useless, so I remove them. If you cannot do this, so in reinforcement learning, what do? You try to play the game at random, which means that basically you randomly sample a trajectory. And then you learn based on your past experience. Hopefully, after several trial and errors, you have explored all of the possible states. Or, obviously, also in reinforcement learning, there is the exploration problem. So the problem that if I want to explore exhaustively all the states, I fall back to the computational problem of optimization techniques. So also in reinforcement learning, you have ways to better navigate the space. Okay, but that's the main difference between reinforcement learning and any other thing, so optimization. You don't know the reward function, you don't know the state transition function. So you need to do basically Monte Carlo sampling, not Monte Carlo search in exhaustive terms. And that's it. There is nothing useful here. So the agents navigate, and this is details about the minimax algorithm that we don't care about. Okay, so best response means this. You assume to play against an equally skilled opponent. If you want to play optimal, he also wants to play optimal. As I said, best response is a family of properties, actually. Two properties that are very well known in game theory, but also in reinforcement learning are the Nash equilibrium and Pareto optimality. Okay, let's try to have an intuition about what do they say about the solution we found. The Nash equilibrium says that no agent, amongst the many possible agents that are playing the game, can improve its own expected return, okay, by deviating from its policy. So I learned a policy, okay. I can't obtain a better return without deviating from the policy, so without changing my policy, given that the policies of other agents stay fixed. So again, before going to the next sentence, let's try to understand that. I am an agent that is learning a policy. I play against other agents. If I assume that the other agents already learned their policies, okay, if our policies are in a Nash equilibrium, okay, if they are in a Nash equilibrium, this means that I have no chance of improving my expected return without persuading other agents to change their policies. That's what it means. Okay? If our policy, so if the joint policy is a Nash equilibrium, any individual agent has no chance to get a better expected return unless it can persuade at least another agent to modify the policy. That's it. A corollary to this definition is, in other words, if a joint policy is the Nash equilibrium, every agent is playing best response against every other agent. That's a corollary. If I cannot get a better return without changing your policy, it means that we are all playing best response. Let's do an opposite example. If by changing my policy and only my policy, not your policy, I can get a better return, this means that I was not playing best response and our joint policy was not Nash equilibrium. I was playing suboptimally. Okay, that's what Nash equilibrium tells you. Pareto optimality is a slightly different thing. keep in mind that let's say to understand better the Pareto optimality and the difference, because at first sight they may seem almost the same. They may seem extremely similar, but they are not. The Nash equilibrium tells us nothing about whether any individual agent got its maximum possible expected return. If you recall the Prisoner dilemma, the Nash equilibrium was the fact that was not the maximum achievable expected return. The Nash equilibrium only says every agent is playing best response against every other agent. This has nothing to do with the expected return of each agent, with the optimality of each individual expected return. A Pareto optimal joint policy instead, so a joint policy is defined to be Pareto optimal if no other joint policy, so we are looking this time at the policies all together, so there is no other joint policy, so no other combination of policies that can give a better return to at least one agent, they can be more, but at least one, without making at least one other agent worse. This tells us something about the expected return. So, a Pareto optimal joint policy means if I want, so let's turn it around. If we are in a given joint policy and the only way I have to improve the expected return of any agent, any of you or me, doesn't matter. So let's assume me. The only way I have to improve my expected return is to make at least one of you worse. We are in a Pareto optimal joint policy. Instead, if I can improve my expected return without making any of you worse, we are not in a Pareto optimal joint policy. I can improve without degrading your performance. They do sound similar, I know, but they are different. Keep in mind these two, keep in mind why they are different. Now, in the Pareto optimal definition, I didn't say anything about your individual policies. I didn't say a word about your individual policies. I defined our joint policy. In the Nash equilibrium, instead, okay, I mentioned the specific policies. So, a Pareto optimal joint policy, in a Pareto optimal joint policy, as I said, if I want a better return, I need to make one of you with a worst return. If I'm not in a Pareto optimal joint policy, instead, I can improve without making you worse. You can have a Pareto optimal joint policy even if you're not in a Nash equilibrium. This depends on the game. Okay? But you can have a Pareto joint optimal policy even without having a Nash equilibrium. They are two similar, but in a sense complementary definitions. The Nash equilibrium talks about the policies of individual agents. The Pareto optimality tells about the expected return of the agents. Okay? There is no mention on deviating the policy. You can deviate the policy here, obviously. Okay? If a joint policy is Pareto optimal, it means that you can deviate your policy anytime as you want. You won't get any better return without making any other agent worse, regardless of whether the other agent policy stays fixed or changes. We don't care about the policies here. In Nash equilibrium, we only care about the policies. So these are two kinds, okay, just two examples of additional properties you may want in your system. Okay, practical example. Why do may I want to have a Nash equilibrium in my multi-agent reinforcement learning? Well, let's imagine that I have a problem in which agents are in a competitive scenario. I want to train my agents to be robust to good opponents. I want to teach my agents to play against the best possible players. Okay, so I want an Nash equilibrium. I may want an Nash equilibrium. I want to guarantee that the other agents that are opposing me cannot do any better without making me change my points. Pareto optimality instead tells me it could be a property useful to have when I want to be sure, for instance, that all of my resources are used as best as I can. An example of Pareto optimality is, let's assume you have some money. You are a company, you have some money, you must decide whether to spend this money to increase the production of either of two products. Okay? Obviously the two different products have different revenues, different costs, different energy consumptions, whatever. Okay? And you have, for some reason, two reinforcement learning agents that control the production of each of these two items. In this example, you care about achieving a Pareto optimal joint policy because you want to make sure that whatever the combination of items you produce, all of your production capacity is used. Okay? So if you reward agents based on how much do they produce, you are happy if none of the two agents can increase its production without making the other agent decrease it. This means that your full capacity is used. So, obviously, there are many Pareto optimal joint policies. I can decide, for instance, to exploit all my capacity for one product. Or I can decide to use all my capacity for the other product. Or I can decide any combination in between, given that I always use my full capacity, for instance. Okay? So we have, in this example, a collection of Pareto optimal joint policies. And what we care about is any of those, for instance. For sure, we want to avoid the situation in which I have some machinery that is unused. Okay, I want to maximize my revenue, so let's use all the possible machinery. That would be a Pareto optimal joint policy. Again, these are simply examples. There are many more examples. For instance, the two properties that I mentioned in the previous slide, fairness and welfare, are properties that wants the expected return of individual agents to respect some constraint. Okay? For instance, in fairness, we want that the average expected return is the same. So we don't want any agent to be too much worse with respect to the other agents. That is, for instance, a property that is useful in real-world problems such as fair allocation of resources. This is something that may sound abstract. Instead, this is the problem of establishing fishing areas and fishing time windows. If you fish too much and you catch all the fish, it takes much time to replenish the fish. Okay, so these kind of decisions can also be taken with this sort of approaches. So something very practical. The same is for the exploitation of land usage. Okay, how much land do I keep for grazing? How much land do I keep for instead agriculture? How much land can I afford to use to build cities? Okay, these are all these kind of decisions. Okay, now, so we mentioned it. Okay, we have some properties that we can define in our solution. You are not obliged, okay? there is much literature even about multi-agent reinforcement learning that simply tries to find some good solution, and this stems from the fact that usually you use reinforcement learning when exact methods fail. So you start by already knowing that it will be difficult to achieve optimality or even impossible. So how can we actually compute a solution? Well, to actually define a learning process, you need 4 ingredients basically. The game, or environment, or decision process, okay, call it whatever you want. So basically you need a model of the environment that the agent will interact with, and also to define what are the interactions. So what are the actions that the agent can do, and what are the observations that the agents can get from the environment. And the reward those. Then you need some data. This is maybe a bit weird because we never spoke about data here. Well, reinforcement learning is different from supervised or unsupervised machine learning, but not so different. It relies on data to learn. What is the data? Well, simply the data is all the collection of states and rewards that the agent experienced while training. So the only difference with supervised and unsupervised learning is not that reinforcement learning doesn't need any data. It needs data. The difference is that it is the agent that generates the data. In supervised and unsupervised learning, you already have the data, and your algorithm can rely on the data without producing new data. Here instead, the data upon which learning happens is generated by the learning agent itself, by the learning model itself. Then obviously you need an algorithm that, based on the data, improves your policy, hopefully towards optimality, and then you need a goal. In single-agent reinforcement learning, the goal is always to maximize the expected return. In multi-agent reinforcement learning, it is to maximize the expected return plus, possibly, some additional properties on the joint policy, on the equilibrium, on the average expected return, whatever property you want. So there are always these ingredients. Basically, you need to define the state, action, and reward. You need to decide which algorithm to adopt, and then you need to decide whether your algorithm needs to achieve a specific goal. The goal part, the goal ingredient, is similar to deciding the performance metric to score, to evaluate your supervised learning model. Do I want a model that optimizes for accuracy, for precision, for recall, for a combination of them? To actually evaluate this learning process, like we evaluated our supervised learning model, there are basically 2 different approaches. One is easier, the weak one. Just, for instance, plot whether the agent is learning or not. So, assuming that your reward function is correct, just plot the reward accumulated over training sessions. If it increases, the agent is learning something. The problem is that maybe you are not sure whether the agent is learning the optimal policy or how far it is from the optimal policy. But at least you can check that the agent is learning. A stronger instead evaluation would be if you have a ground truth about what the optimal policy is, compare your agent learn policy against the optimal policy. Okay. Actually evaluating the learning process most of the times is easy. Let's assume that you are training an agent to play Super Mario. Your evaluation would be how long does it take for the agent to achieve the end of the stage. That could be an evaluation method. The faster it is, the better it is at playing. Another one could be how many coins it gets. Okay, it could be the more the coins, the better it is. Probably the best would be a combination of the 2, because you don't want only to farm coins. You also want to reach the end of the stage. So probably the reward function should somehow take into account a combination of the time to complete the stage and the amount of coins collected. Something like that. Okay? So, if you want to clarify better all of these ingredients in our usual schema, defining the game will be defining what are the states of the environment, their transitions, and also define how the environment interacts with the agent. So, what is that the agent can perceive of the environment? What is that the agent can affect through actions in the environment? This will be the definition of the game. The data that the agent uses, or better, the algorithm, the reinforcement learning algorithm uses to learn, is the collection of observation and rewards. The algorithm should update the policy, and the goal, for instance, is to get to an optimal joint policy plus some desired equilibrium. Okay. So now, we don't go into the details of specific multi-agent reinforcement learning algorithm. Why do we need reinforcement learning algorithm specifically conceived for multi-agent scenarios in the first place? Why can't we simply adopt reinforcement learning algorithm like the Q-learning that we have seen? No? Let's try to understand why. In multi-agent reinforcement learning, you basically have, let's say, 3 different learning modes, paradigms. There is no specific terminology here, okay? So reading different things, you find different terms. I'd like to speak about learning modes, learning paradigms, stuff like that. So, given that you are in a multi-agent world, you can take, let's first examine the 2, let's say, extremes of these 3 approaches, okay? That in fact are more than 3, but just to understand. It is a spectrum, in fact, between 2 extremes. So, if I have multiple agents, I can take my approach could be one of 2 extremes. Either I consider each agent in isolation. So I have 10 agents that are learning. Okay. Each agent learns by its own, basically. It has its own observations, it can do its own action, it takes its reward. It doesn't care about other agents being in the environment. Okay? That will be called independent learning, one end of this spectrum. Each agent doesn't care about the others. Obviously, the opposite spectrum would be, no, let's wait. Since we are 5 robots that need to manage this warehouse, let's try to collaborate during learning, okay? So, for instance, if I learn that by going full speed in this corridor, there is a high chance of crashing into the wall, let me warn other agents about this thing that I discovered, okay? So let's somehow communicate to the other agent, look, I crashed into the wall, I hurt myself, so don't do this action if you are in this state. If all the agents, okay, communicate with let's say a central controller, a supervisor, this sort of information, and the supervisor is the one in charge of telling the agents what to do, we are in a centralized learning setting. The exact opposite of independent learning. Why the exact opposite? Here, all of the agents are cooperating through usually a central point of computation, and this central point commands all of the agents. Obviously, as we said, these 2 extremes define a spectrum in which, depending on what information do the agents share, with whom, when, stuff like that, we are in a gray area. We are not doing completely independent learning, we are not doing completely central learning, we are doing something that in the literature is known as CTD, centralized training, decentralized execution. And in a few slides we will see better what it is. But let's first understand better the two extremes. So, independent learning means if I have 10 agents, I am actually training how many policies that can potentially be different. 10. Every agent is on its own. So I have 10 software controllers, 10 implementations of the learning algorithm, and in principle, each of these agents can come up with a different policy at the end of training. Okay? Nice. Easy to understand. Everybody on its own. What are the benefits and drawbacks of this approach? Well, the first big benefit, or at least the fact that we must consider, is that by doing this, each agent on its own, the other agents, I don't care about them, we are actually reducing the multi-agent learning problem to a single agent. The agent only cares about itself, doesn't care about the others. From the perspective of the learning algorithm, it is a single agent problem. My agent needs to learn. So, the first benefit that stems from this fact is that in an independent learning multi-agent setting, I can simply reuse any existing single agent reinforcement learning algorithm. Every agent is on its own, they don't care about each other, they don't cooperate, they don't do anything, they only learn from their own experiences. I can reuse any kind of single agent learning algorithm. Pure learning, whatever you want, SARS, whatever. The input and output of this algorithm, what will it be? Well, for each agent, the agent only gave its own observation and its own reward, and the output of the algorithm is, for each agent, only compute the action that that specific agent has to do. No? Okay, wonderful. So, always do this. The problem of doing this is that we are doing nothing to mitigate the three big challenges of multi-agent reinforcement learning. Non-stationarity, so moving target problem, equilibrium selection, and credit assignment. They don't cooperate, they don't talk to each other, they do nothing together, everybody's on its own. So, let's examine the three challenges. I try to recall. Moving target. So the problem that the environment is no longer stationary. That's true. I am one agent that is learning, but in an environment in which other agents are learning too. So this means that the policies of the other agents are always changing, as mine. They are learning. So, if in my previous step, in a given state, I did one action and got a given reward, in the future, in the exact same state, doing the exact same action, I could get a different reward. Maybe a long time ago, to get a specific item on a shelf, I went in a straight line. And I got my reward, I got to the item. After some time, I am requested to pick up the same item. I go in a straight line and I crash with another robot. My policy did not account for the other robot. I'm not caring about the other robot. They are parts of the environment. Okay, so this means that the environment is no longer stationary. The transitions changes depending on what other agents are doing. So we have the moving target problem. We have the credit assignment problem. I have 5 agents to manage my 5 robots to manage my warehouse, and what I only do care about is getting items that I ask to the agents, to the robots, to the counter, to a given delivery point as fast as possible. What if out of 5 only 2 agents always go back and forth and the other 3 do nothing? That's not an ideal situation. I mean, it means that either I can spare the other 3 robots, so to serve my current needs I only need 2, or my ensemble of 5 robots is far away from the optimal joint policy because 3 robots are not utilized, right? So I have a credit assignment problem. How can I distinguish the reward that I give to each agent? You did something, so you get a reward. You did nothing, you get a penalty. Okay? And again, we can do the same reasoning for equilibrium reward. So, the good news about using independent learning is that we can reuse any kind of single agent reinforcement learning. We don't care about whether we have some sort of constraint in our application domains. No. In this specific domain, in my factory, in my problem, the agents cannot communicate. Who cares? They weren't meant to communicate anyway. And a more technical problem related to the computational complexity, each agent only cares about its own policy. We don't ever consider the joint policy. So we don't have any problem about combinatorial explosion of the action space, because we don't need to combine the different policies. Each agent only cares about its own policy. Obviously, the bad news, as we said, is that we are doing nothing to mitigate the typical issues of multi-agent vertical. So, what is the takeaway lesson? Can we apply independent learning in multi-agent reinforcement learning? Yes, always. In general, do not expect very good results because of all of these issues. But you can always do that. And in fact, the starting point many times is, okay, let's try independent learning first. Maybe it works. And so we don't need more complicated, sophisticated algorithms. We don't need communication. Okay? So it can work, but typically you lose any kind of convergence guarantee, you lose any kind of optimality guarantee, stuff like that. So you can view independent learning as this, okay? You have multiple agents, each is on its own. Its own observation and action, its own reward, its own policy. This slide is just about terminology, because if you read some paper you can find often this terminology taken for granted. What does it mean? We trained our agents in a self-play setting. It means that actually it may mean 2 things, and oftentimes it is not specified, so you need to try to figure it out. Self-play generally means that the agents are all the same. They are homogeneous. In practice, okay, more specifically, what does it mean? You have 2 interpretations, a stricter and a looser one. In the first interpretation, we simply intend that all agents use the same learning algorithm with the same parameter. So I have 10 agents, I'm using independent learning, all of the 10 agents use co-learning, with the same learning rate, with the same discount factor, whatever. A stricter interpretation instead would be that the agents use the exact same policy. So they learn the exact same policy. Mixed play instead means that we can have heterogeneous agents. So we can have a pool of agents, each with its own learning algorithms, whatever. Again, this is just about the terminology you may find. So let's try to get a practical, okay, insight about what does it mean to do independent learning. So now there are a few examples, and you have the link to the code repository, that compare independent learning, fully centralized learning that we yet have to completely define, and one solution in between. Okay? To see what we can expect, not much what it changes on the, let's say, algorithmic side. You have a full implementation, okay, of an algorithm, but I don't need you to look at it because it may be quite complicated. Okay, so you have it if you want, but it may be a bit complicated. Okay, you use an external library, so you need to learn about that library, stuff like that. So it is there mostly as a blueprint. Okay, what can you do, or for the curious guys. So before delving into the specific example, let's define central learning. So we have defined independent. What is the other side of the spectrum? Well, if we do central learning, it actually means that regardless of how many agents do we are actually training one policy. We want only one policy that commands all of the agents. No, it's like the Lord of the Rings, one ring to rule them all. That's the same, one policy to command all of the agents. If we do this, again, we can say that we reduce the multi-agent learning problem to a single agent learning problem. In a very different way, I agree. But we can say the same. It is still, from our perspective, from the learning perspective, we again reduce the multi-agent learning problem to a single agent problem. There is only one learning algorithm that only wants to learn one optimal policy, but this policy is the joint policy. It controls all of the agents. So again, let's try to understand what are the implications of this, because we are, as in independent learning, we still reduce the problem to single agent setting, but in a very different way. This time the learning algorithm as input, first of all, there will be only one policy, not n policies. So one only learning algorithm. The input is the concatenation of all the observations of all the agents. And the output is the joint action. So the concatenation of all the actions for every agent. So if in independent learning each agent has its own policy that only tells the agent go up, go down, go left, go right, in centralized learning, fully centralized learning, there is only one policy, and the action is, the joint action is, agent 1 go up, agent 2 go down, agent 3 go left. Okay? Again, what are the benefits and drawbacks stemming from this interpretation of the problem? Again, we can reuse any kind of single agent algorithm, like in independent learning. But this time, it is not so easy, because we need to translate all of the, let's say, all of the ingredients of the learning algorithm from an individual agent setting to a joint setting. So for instance, I need to come up with a reward that considers the joint action of all the agents. I need to come up with a joint observations vector, okay? I need to come up with a format to represent joint actions. So I need to do a little bit of work. Since I need to build a joint action, so I need to tell every agent what it has to do, this time there is a high risk that the joint action space grows exponentially. If you have 10 agents and every agent can choose amongst 4 different directions, and your state space first of all, your joint action space is for every agent telling the direction where to go. So you have 4 actions times 10 agents combinations. In the independent learning setting, you don't have this problem. Each agent is on its own. The action space is the same. Each agent only has 4 admissible actions. The state space suffers from the same problem. If your state space is only, I don't know, whether there is another agent in my nearby cells. If you are in a centralized learning perspective, for any agent, you have a state space in which every possible combination of there is an agent is the cell up north, the cells in the south, the cell in the west. So again, you have a huge state space. In independent learning, no. Each agent has only its 4 adjacent cells. So in this case, you may have this computational problem. Another benefit, instead, is that by modeling the problem in this way, typically, you don't have the typical challenges of multi-agent reinforcement learning. Why? The moving target problem is no longer there because you are commanding all the agents. So the environment is still stationary. There is no other agent that I'm not considering that can mess up my environment. All of the agents are controlled by me. If I mess up the environment, it's my fault. That's it. You can do credit assignment. I know if one agent is not doing anything to contribute to the goal. I am controlling that agent. And I can also do equilibrium selection. I am shaping the reward function for all the agents. I can take care of balancing, for instance, the contribution. So if one agent achieves the goal, do I do a reward also to agents that didn't contribute to the goal? Maybe not. Instead, another drawback may be that if you have some sort of domain or computational constraints, you may not be able to use centralized learning. For instance, if you don't have ways for your robots to communicate with a central server, you cannot apply this sort of approach. Central learning obviously can be imagined like this. You have one big brain, okay? One algorithm that learns one policy that gathers all of the observations and commands each agent. So the complete opposite of the independent learning set. So now after the pause, we will see in practice these 2 examples, and we will also see what may go wrong with centralized learning that make actually, if you do fully centralized learning, usually this is not the correct solution, but you need to resort to this gray area that we call CTD, so centralized training, decentralized execution. Another